Hello students, welcome to this last lecture in magnetic fields in matter. In the last lecture, we learned that the effect of magnetization is essentially to establish the bound currents. Bound currents, that is your JB, which was nothing but your curl of M, KB, the bound surface currents, which is nothing but your M cross M cap. Now, the field produced by the magnetic material is nothing but the field produced by these bound currents. But in the material, you can also have free currents like other currents, except these bound currents. For example, you can embed a wire in that material and pass a current. So those free currents will also contribute to the field. Essentially, we can write the total current as a summation of the bound currents, which was produced by the effect of the magnetization, and any free current flowing in the material. That is that I call as JF. JF is nothing but free current, and JB is the bound current. The total current is J. Now, if you want to write the Ampere law, so you know the Ampere's law is del cross B is nothing but mu 0 J, where J is the total current. But you know this J in magnetized material will have contributions. One is from the bound current, one is from the free current. So your Ampere's law now becomes del cross B is mu 0 JB plus JF. And you know JB is nothing but del cross M, so you can rearrange, and then what you will find out, your Ampere becomes plus 1 over mu 0 B minus M equal to JF. Okay. So I'm missing the arrow sign. Yeah. So now, in the parentheses, we can designate that as H. And H now we are saying that over mu B minus M. Okay. So if you do that, then you have a very simplified form of Ampere's. That's your del cross H is nothing but JF. So this is what I call as the Ampere's law. This is what is called as Ampere's law in magnetized material. So that is del cross H is nothing but JF. Remember, JF is nothing but free currents. You can now express of integral. Okay. So that is what the free current enclosed by the Amperean loop. Okay. Now this H, you might remember you did a similar analysis in case of electrostatic, where you did where you use the displacement vector D. So H plays a very similar role as D in electrostatics. Okay. So what H does is that H permits us to write Ampere's law in terms of free current alone. And the free current is the one which you control. Okay. So which means H gives you an easy way, to calculate. If the symmetry allows you, you can calculate the field using H because you know the free current. So as a simple example, let's consider our familiar example, which is a wire. So here there is a wire, a cylinder, and let us say that there is some magnetization M along Z axis. So this is my Z cap axis. So we have an cylinder with uniform M. So M is your uniform along Z cap. The question is, what is the magnetic field B? Now, at the outset, you notice that there are no free currents here. Okay. So since there are no free currents, your JF is 0. And if you employ this Ampere's law integral from, H dot dl should give you 0, right? Because there are no free currents. So H dot dl should give you 0. And in that case, your H is also 0. Okay, that you can, you have done all those this kind of similar kind of calculations. So using symmetry you can see. So your H is equal to 0 and H is nothing but your E over mu 0 minus M. So you're effectively, you now have B, which is mu 0 M. Okay. This is the result which you have also obtained earlier. Okay. So the same thing you obtained, but in a much quicker and easier way using H. We can take another example where there are free currents. So let's take this here, okay? But instead of magnetized, we are saying that there are now free currents. So earlier we said there are no free currents. So now we are saying there is current I which is flowing along Z axis, along Z cap, okay? So now your H dot dl is nothing but your I enclosed, okay? So I enclosed is nothing but whatever total current is I here, and for that, so if you want to calculate the B inside the cylinder, so let's start a distance S from the center, then H dot dl is nothing but H 2 pi S, because H is uniform, so you just take out the H and then you have the dl integration that gives you 2 pi S. And IF enclosed. So what is the current enclosed? So the question is, what is the current enclosed in this particular area? In this particular area, what is the current? So total current is nothing but I. Okay. And that is flowing through pi r square. So how much current will flow through this particular area? That is your pi square. So the current which will flow through this will be nothing but pi square multiplied by I by I square. Right? Total current is I, that is flowing in a radius R. So let me say this radius is R. So which means the current flowing through this Amperian loop. We are constructing an Amperian loop, what is pi square. The area is pi square for that loop. So the current flowing through that area is pi square multiplied by I divided over pi r square. And that's what I have written here. Then you do algebra there and you eventually find out H is equal to I pi 2 pi r square is phi cap. Okay, that's very intuitive to see. And that is where your S is less than equal to R. Now, what happens if your S is greater than equal to R? It's very simple, because you have your I total current, you have nothing else. So the Amperian loop constructed outside this cylinder will enclose the total free current as I, nothing else. So that's easy to write now. That's why H is equal to I over 2 pi S phi cap. What about B? So to calculate B, you should know what is M, right? Because because there are no magnetic material outside, so your M is 0 outside the cylinder, because our problem states that there will be no magnetic material outside the cylinder, for which means there will be no magnetization there, right? So your M equal to 0 outside the cylinder. And for that reason, now you can write H equal to B over mu 0 minus M, where M equal to 0. So H is equal to B over mu 0, which means B equal to mu 0 H. That is your field outside. Okay. And that B is nothing but, again, you can write real, so mu 0 I by. Okay. That's your outside field outside. Now, what about inside? Now, inside we are not giving any idea about, we don't have any idea about, since we don't know M, so we cannot calculate the B inside. Okay, so we can only know the B outside. So next we go to the boundary conditions in H. Now that's very easy to see. You have already done similar analysis in case of your electrostatic, as well as in case of the magnetic field B and the potential A. So to determine the boundary conditions, we use two equations. One is your del cross H, which you already know, the Ampere's law, which is nothing but JF. Del dot H you can calculate from this expression. So your del dot H is, so your H is what? H is nothing but B by mu 0 minus M. Now if you calculate del dot H, there's all vector here. So which is nothing but del dot B, which is 0, minus del dot M. So that's why this part is 0. So you're only left with minus del dot M. Okay, so that's what I've written here. So I'll erase this part. So your divergence of H is nothing but minus del dot M. So using these two equations, you can determine the boundary conditions. And again, you go through the similar procedures of constructing a pillbox, then calculating what is the discontinuity in H above the parallel and the perpendicular component of H. I will not really go through them. I mean, I have already told you the two equations which you can take the help of these two equations and determine. You will find out that the H perpendicular above minus H perpendicular below will give you M above minus M below. So that you can use this equation, del dot H minus equal to minus del dot M, and then you can construct a pillbox and then calculate the H perpendicular above and H perpendicular below. And that discontinuity is given by minus M perpendicular above minus M perpendicular below. Okay. Similarly, you can construct a loop and then calculate the H. So from the first equation, del cross H to the F, and that you can calculate the boundary condition for H parallel, and again that you will find out F cross and cap. So please see, I mean, use your previous learnings from electrostatics case, even for the magnetic field case, and you can arrive at these boundary conditions. Okay, next I shift my discussions to linear media. Okay. So what do I mean by linear media? Before I begin the discussion, so first please note that in paramagnetic and diamagnetic material, whatever we have discussed so far, the magnetization actually is sustained by the applied field. So you apply the field and you have a magnetization, you remove the field, you make the magnetization zero inside the material, right? So as long as there is B, you will have the magnetization M. You will remove M. Okay. So in other words, you can say that your magnetization is proportional to the field. Then you can write equality with write the equality of magnetization with respect to field with using a proportionality constant that we call as chi m. So now you can write M is nothing but chi m H, where chi m we call as magnetic susceptibility. And this obviously will be positive for paramagnetic because the alignments are along the field or parallel to the field. And the chi m will be negative for diamagnetic because, as you know, magnetic magnetization is opposite to the field. For that reason, chi m will be negative. Now you know H is equal to B over mu 0 minus M. So now if you calculate B, you get like mu 0 H plus M, which is nothing but mu 0 H in place of M, you write chi m H. And that essentially gives you mu 0 1 plus chi m H. And this 1 plus chi m write as in multiplied mu 0 as mu. That we call as permeability. So if you do that, then you have B equal to mu H, which means B is proportional to H. So for linear media, that's a very important thing. Linear media, B is proportional to H because you can write B equal to mu H. Where mu is now mu 0 1 plus chi m. That's your permeability. So in fact, since there are no material to magnetize, your chi m equal to 0. So mu will be mu 0, which is permeability of vacuum. Okay. So the media, the material which obeys such relation B is proportional to H are known as linear media. Okay, the medium which where you can write this kind of proportionality relation between B and H, you can call them as linear media. Now, what about nonlinear media? We'll take an example. So, we'll discuss now the ferromagnetic effect. Okay, the ferromagnetism. So, first thing, ferromagnets are not linear. Okay, so they are the examples of nonlinear media. Now, like the case of paramagnetism, ferromagnetism also in spin of unpaired electrons that you should know. So in paramagnetic case, you know that the spin of unpaired electrons plays the important role there. Here also, spin of unpaired electron is important for ferromagnetism. So what is difference between what is the different thing happens here than the paramagnetic case? So here what happens? There is some mutual interaction between nearby dipoles, and those interactions are quantum mechanical in nature. So I'm not going to discuss that here. So once you have interaction between the, let's say, neighboring dipoles, then you will have a strong tendency to align similar to the neighboring dipole, and that is what is responsible for your ferromagnetic effect. So although the correlation between the spins are very strong, the alignment is not doesn't occur like across the whole material in a similar fashion. Instead, it happens in patches, and those are known as domains. Okay, so those are known as domains. Okay, so each domain will contain will have billions of dipoles. Okay, so and inside each domain the alignment is perfect, right? So if you want to have a very crude picture of what I want to say is the following. So let's say there is a ferromagnetic domain, ferromagnetic material, and you have many domains like some here, and then there is a domain here, and each of these patch, that can be many different ways the domain can have. So let's say you have one patch here, and then this will have a preferential alignment. So let's say, let me put this. Okay, so let's say this has alignment like that. Similarly, this domain can have alignment like that. This can have alignment like that. So all those domains, although each domain contain billions of dipoles, which is aligned in a particular way, giving rise to a net alignment for the domain, the domains themselves are aligned randomly. So in the absence of field, so when B is not there, B is 0, this is what happens. Okay, so then you have all sorts of possible alignment. So the net alignment is 0. Okay. Now if you apply the field, so then what happens is that they will apply it on individual dipoles. Okay. So because of the torque, the domain alignment which is nearly parallel to the field will be favored, meaning that is where the torque will be least. So those domains, let's say the field is applied along this direction. So the domains which are more or less aligned along the same, very nearly aligned along the same direction will start growing. So let's say this domain, and if there is another domain which has same alignment, will start growing. So these will grow in expense of the other domains which are not aligned along the field way. So then the domain boundaries, so those domains which are not aligned along the field will shrink. The domains which are aligned along the field will grow. Thereby, you may have the one domain can literally grow and cover the entire system, and you have a one particular element like that. And that is when B is applied. So B is not. So if the field is very strong, if the field is very strong, this will be like a perfect alignment, and all the domains will be like the whole system will be occupied by, will be preferentially oriented along the field direction. And then you can have literally, you can think of as one single alignment. And that is why you call it as saturated. Okay, there are no more domains which are not aligned along the field. Everything is aligned along the field. Okay, you can have a literally a single domain for the when one domain can take over the material entirely. Okay. Now once you then you gradually reduce the field or turn off the field. So then what happens? What do you expect? Do you expect them to come back to the original state? Actually, no. Okay. So they are, when you turn off the field, this is not, and they don't entirely reverse, in the sense there will be some alignments which will be kind of destroyed, but not entirely, which means there will be a residual magnetization or remnant magnetization. Okay, so some domains will return to the randomly oriented domains, but it still, you will have some magnetization left over. Okay, some magnetization will, it will remember the history of alignment. Okay, so thereby you will not entirely reduce the magnetization to zero. That is what makes this ferromagnetic material different than the other like para or diamond material. So they retain some amount of magnetization even when the field is switched off. So this usually gives it something known as, so this kind of memory effect, or the magnetization depending upon the history gives rise something known as hysteresis loop. Okay. So I just have a very simple explanation for that. So let's say you have a hysteresis loop. Sorry, hysteresis loop. Okay. So let's just think of so one of the example of a ferromagnetic material is iron. So now what you think is that, let's think there is an iron rod and you have some coils and you are passing a current I here. Okay, using some battery. Okay. So when you increase the current, so now if I want to plot the magnetization as you increase the current, so as you increase the current, you will have a magnetic field which will magnetize the iron. So let's say you have, okay, hold on. So let's say this is my I, this is my magnetization. So that's a simple experiment. You are passing current, which will magnetize the iron. So initially you are at 0. So you start with something like here, okay, and then you increase the current. So as you increase the current, you have some sort of a magnetization. And as I told you, if you increase the current to a very large value, you will reach the saturation in magnetization, right? So because one domain will cover the entire, so you will not have any more further increase in the magnetization, so that you need a saturation. So once you have that, now you kind of reduce the field. So you start increasing, you have this. Now when you reduce the field, it doesn't traces back the same path. So because there will be some residual magnetization, so it will follow something like that. Okay. So as you keep on reducing the field, this and then make it 0. So at field 0, there will be some magnetization left over. So in order to kind of make it total, make it 0, you put the current in a reverse way, and then you can make it 0. Okay, so if you apply current in the reverse way, then you will make the total whatever residual magnetization, you can kind of make it 0. And then as you increase the current the negative way, you will have the saturation, the alignment along the opposite direction, that also will have a saturation. Okay, at certain amount of negative current. Again, you reduce the current or increase the current. So from negative, you make it to 0. And when you make it to 0, you still have some magnetization left over in the opposite direction. Okay. Then further you increase the current to make it 0. And then you again increase and you will increase the saturation. So this is what we call as hysteresis loop. So one bottom line is that your state of magnetization in ferromagnetic material depends upon history or how it has been magnetized. For example, if you are at a particular value of current here, let's say you are at this current level, you see there are 3 possible magnetization which can be possible at this particular current, right? So I want to make it that. So for at this particular, you have 3 possible, one here, one here, one here. So if it depends upon how, from where you are starting and to reach this particular I. Depending upon that, if you start from here, then your magnetization will be this one. And if you start from other points, your magnetization can be this one or this one. Okay. So that is what the ferromagnetic material look like. Now, one last point about ferromagnetism is that since you can kind of kill the alignments using temperature, so the dipoles within a given domain, they kind of align parallel to one another. And if you have thermal motions, they actually compete with such kind of ordering. So if you increase the temperature beyond certain value known as Curie point, you will destroy the alignment. So if your temperature is greater than Curie point, so you will destroy the alignment. This will give rise to paramagnetic behavior. So for iron, it happens in 770 degree centigrade. So beyond that, your ferromagnetic material will be like a paramagnetic material. Okay. Now, once you come below Curie temperature, it will again become the ferromagnetic effects will be more prominent. Okay. Okay, so actually that's all I wanted to discuss in magnetic fields in matter. So I hope you have got a good amount of idea about magnetic field and how the field, how to look at the magnetic field for the case of magnetic materials. So if you have any doubt, we can discuss them in the discussion classes. So thank you very much.